Okay, welcome everyone to Map Time Davis. I'm so excited because today is our first workshop of the new school year. And this has been a long time in the making. Our new Map Time Davis Council has been working really hard to get a really fantastic lineup of workshops, and today is no exception, so I'm really excited. For those of you who are new to Map Time, if you've never been here before, really quick intro. Map Time is essentially a group of people who are interested in making maps. It's literally time for making maps, and there are chapters all over the world. We are just one of many, and each one gets to have its own focus, and ours being affiliated with the university, we tend to be a little bit more research oriented and tools that appeal to doing research and analysis, but you are welcome to visit other Map Time chapters throughout the world, and they'll have their own kind of preferences and flavor to what they present and what they do. But I'm really glad you guys are here. We have some really cool stuff coming up in the next few weeks, actually throughout the entire quarter. So next week, so this week is a fairly advanced workshop. We expect that you've got a certain level of skills. If you don't worry, sit tight. You can still learn a lot. Next week is going to be a very introductory workshop. So I'm going to be presenting a workshop that I call Is My Research Mappable? So if you have colleagues that are interested in getting their feet wet with GIS and spatial data, this is a really good workshop. So when you see the announcement, forward it to people who you think might be interested. We're going to give people some skills to just get started if they're new. After that, the following week on October 19th, we're going to be doing interactive maps in R Shiny with Taylor Nelson. That should be a really good workshop if you're interested in learning how to work with Shiny and how to work with spatial data in that. The next 2 weeks after that, we've got a couple of ArcGIS Esri workshops, getting started with ArcGIS Online and ArcGIS Field Maps. Followed by PostGIS with Crunchy Data. Crunchy Data's got a really awesome tutorial for PostGIS, which is a spatial database. So if you're interested in that kind of stuff, I've been through the materials there. It's fantastic. I'm really looking forward to that workshop. And then finally, we're going to wrap up the whole thing on November 16th with Introduction to Desktop GIS with QGIS. So again, if you've got colleagues who are new, or if you yourself are interested in learning about desktop GIS, that final workshop is going to be a really good one for beginners as well as people looking to learn QGIS. So you can see we have a really wide range of topics this quarter, and I hope you'll join us in the upcoming weeks for some of our really awesome workshops that we've got coming up. I realize I never introduced myself. My name is Michelle Tobias. I am the geospatial data specialist at UC Davis Data Lab. We do data science and we help people with their entire data pipeline for research. So we also have things like, aside from workshops, we do drop-in hours. Now they're on Wednesdays from 1:30 to 3. If you're interested, you can find out more on our website, which is datalab.ucdavis.edu. So that is a lot of things in general. Today, I am really excited to have our speaker, Lucas, who is going to be presenting a workshop entitled Accessing Cloud-Hosted NetCDF with Python via Zar Turbocharged with Reference File System. And I'm super excited about this workshop because NetCDF is one of those questions I get pretty frequently, and I'm really looking forward to understanding this better. So I'm going to hand it over to Lucas to start the workshop.
Thanks, Michelle. Hi, everyone. I'm Lucas. I'm a, fifth year PhD student at UC Davis. I am in the Atmospheric Science Graduate Group. I study clouds, I do cloud modeling and stuff. So, I'm kind of separate from I think a lot of people in this group do like GIS type stuff. That's not really my wheelhouse, but what I do a lot of is kind of these gridded scientific data sets that a lot of which are in HDF5 or NetCDF4. And so that's kind of the underlying motivation for the talk. I'm going to post a link to a GitHub page just to give you the launching point for our workshop here. So if everybody wants to go there, and then I will share my screen, which is, here we go. So this is the GitHub page. If you want to scroll down to the README here, if you can go ahead and click this Pangeo binder link, what this is going to do, it's going to launch. I'll click it here to show what it looks like. You'll see this page. If you click on the log, it'll say it's found an image and launching a server. Within a few moments, you should get to a page that looks like this. Sometimes these icons don't show up right away. Just go ahead and click the little refresh icon right there. And while everybody's getting started and getting that thrown up, I will open up this first file here called 01-create references. At the beginning of this, there's a little bit of like a presentation that I'm going to give. So I'll scroll through this as people are getting set up. Feel free to put comments or questions in the chat. Also, just feel free to interrupt me over voice. That's totally cool. Okay. So this is work I did over the summer at the National Center for Atmospheric Research summer internship in parallel computational science program. And kind of the underlying motivation is a lot of our workflows currently look like this left image. We have some data that we want to analyze. It exists on a server somewhere, an FTP server, an HTTP server, somewhere where we can, or transferring via Globus or something. We have files we want to access. We download those files to our computer, and then we do our analysis on our computer. But these data sets are getting really, really big. And I think everyone here has kind of encountered an instance in which we can't just get all the data on our computer. The download time would be too long, our disk isn't big enough. And with the advent of cloud computing, we can kind of think about this a different way. Instead of moving our data to our computer, we can move our computer to the data. And so a lot of organizations are putting their data in the cloud. And with that, we can start computational servers also in that same cloud data center. And from there, we have really quick access to data stored in that same data center, and a really fast and easy scalable way to get as much processing and as much like actual data workers working on that data as possible. So we're kind of removing our computer from the mix, and it's just a head terminal for accessing that data. And so the motivation behind the project I worked on is NetCDF. If you're not familiar with NetCDF, it's a common format, binary data format to store gridded data sets. So if you work on things that are on a lat-long grid or a model that calculates variables on a grid, you'll probably have come across this format. And so this is kind of a visualization of a single NetCDF file that has different chunks of data in it, and kind of aligned on a grid like that. And for Earth and atmospheric sciences, the type of work that I do, this is the most common data format. And it has a lot of official community support. It's really easy to work with if you know the tools to use with it. But there's a problem. And the problem is that to understand what this data looks like when you want to access it, you need to read a lot. You have to do a lot of little reads to that data. Now, if it's on your hard drive, that's not a huge deal. But if you're, trying to access it over a network on a cloud computing, that slows down a lot. You can also use a server-side utility like Threads or OpenDAP that kind of do server-side processing of this data to extract metadata. But really, we have this single file object. It has a lot of chunks of data in it. We need to do a lot of little processing to gather out where those chunks are, what their size is, what the data we want, where the data we want is located, and stuff like that. Oh, I think we may have crashed Pangeo. That's okay. I will continue this way. If you're getting this error, you can probably keep refreshing it, and it'll probably pop up relatively soon. But I'll continue to present from this until that pops back up. So the ZAR data format, which is a new cloud optimized data format, kind of alleviates this problem. It does it in two ways. One, it takes up this one file with many chunks of data, and it splits those chunks up into individual files. So each chunk is one file. And then it takes all the metadata that normally would take a lot of little reads to generate, and it puts them all into one plain text file. So if you want to access a data set in ZAR, all you need to do initially is read the small plain text metadata file. And in that, it tells you how big the data set is, what variables are in it, how big those variables are, what chunks they have, where those chunks are located. And when it comes time to actually pull data from that data set, it knows exactly which one of these files to pull. But there's a problem with that, and that it requires data duplication. We need to convert our data from NetCDF to ZAR. And if you're someone like Noah, who has GOES 16 satellite data, which is we're going to be using later in this tutorial. Let me try and refresh this one more time. Oh man, guess it could not handle 10 people. If you're trying to run this and it's not working, you can click on this mybinder.org fallback, and that should run. It will be less powerful to run the workshop on, but it'll at least get you into this notebook view. So try that second link if the first one's not working for you. So yeah, while ZAR is good and it really helps in terms of accessing these large data sets quickly, we'd have to convert it. And having to convert, petabytes of data is a big ask. And either we're gonna have to convert it completely and people are gonna lose access to NetCDF, or more likely we're gonna have to duplicate all this data and essentially pay for double the storage. And that's not good. We hopefully can find a different way. So the software I helped work on over the summer is called FSpec Reference Maker. It takes the heavy lifting of figuring out the metadata from this NetCDF file, and it throws it into a metadata file that's very much like the ZAR metadata file. In fact, it uses the same specification, but instead of pointing to individual file objects that are existing on disks, it just points back to the original chunks in the data. And so instead of using the NetCDF API at that point, it just points to a byte offset. So it says, okay, variable 1, chunk 1 is between bytes 0 and 100 in this big binary file. Chunk 2 is between byte 100 and 200 or something like that. And so we're able to still extract these chunks as if they're individual files, but we don't need to go through the process of actually generating the metadata and like figuring it out. That's already been done for us, and that's what this reference maker does. Before we go into an example of how it works, I wanted to show, I tested this on 24 hours of 5-minute GOES 16 satellite data. So that's 144 files. And I accessed it first via just normal NetCDF. I just pointed, if you guys know Xarray, and if not, we'll learn some of it today. I pointed Xarray at these remote files and said, build an MF dataset on this. And then I did stuff like generate a little animation. I did some spatial analysis, a couple time series, just a basic little workflow on this data. With the normal NetCDF4, it took 0 minutes to pre-process because everything existed in the cloud exactly how we wanted it. It took 10 minutes just to open a data set. That was the time that it took to do all these little reads to try and generate the metadata. And then to actually generate the workflow, make the images and plots I wanted to make, it took 40 minutes. But I generated no extra storage. I didn't have to create any new files to get this to work. If I wanted to convert all those files to ZAR, it took about 1 hour and 40 minutes to convert those files to ZAR and upload them to the cloud. But once they were converted to ZAR and uploaded onto the cloud, it only took 30 seconds to open that data set and only 4 minutes to run that workflow, which is a huge improvement over that NetCDF4 method. But the downside is it generated 52 gigabytes of data. That is the same amount that the original data set is. So I duplicated the entire data set. And so that is a huge storage cost. Using reference file system and reference maker, it took 1 hour and 25 minutes to generate the metadata files for that data set. And again, about 35 seconds and about 5 minutes of data set opening time and running the workflow, which is very comparable to ZAR. But the additional files I generated only added up to 416 megabytes. And so we're able to kind of grab the speed of ZAR without actually having to convert any of the data and just have to generate a few plain text files. So let's try it out if I can get this to work. No, I'm going to run this locally because I would like to show off everything. If you're running this out of curiosity, if you want to post in the chat, is everybody actually getting the binder, sorry, the Pangeo one to work, or is it down for everybody?
It's down for me too.
Okay. Well, I think we found, I was hoping that like 15 or so people wouldn't crash Pangeo, but it might be up. So if you want to like keep refreshing every once in a while, I'm going to run this. This is running on my own machine here. If you're on Binder, it's going to look, really had to generate a new. I thought I had generated an image already. Is anybody actually in one of these environments where you can actually run the cells or not? Because if not, I will wait a sec for these services to respond.
Yeah, my screen looks a lot like yours, where it's oh, it's not actually done setting up the image.
Okay.
Building.
Okay. That's weird. I made sure to generate an image before I started all this, but I guess it wants to generate a new one. So if you're on this scene, okay, we're almost done here. I'm guessing it's close to being done for everybody else here. So I'll wait a sec here for this to finish up.
I think you can go ahead and switch to your notebook and kind of show it, and then we'll jump back.
Okay, yeah. So
give people a chance.
Yeah, if people are okay, kind of following along, and kind of catching up, the first little bit.
It might be a good time to ask if there's any questions from the group.
Sure.
You can either feel free to unmute and just ask, or you can put them in the chat and Alex and I can relay them. Just give you a chance to ask.
If there's any questions, I know this is all kind of theoretical, and if you're not super familiar with these data formats, it probably doesn't make a whole lot of sense, but it'll make more sense once we actually get our hands dirty with this. Okay, so everybody is kind of on this Mamba screen here, it looks like. I assume your workflow time is related to actions on the data and slow plotting like Matplotlib. Yeah, so the workflow I was doing at the time, my plotting with Matplotlib, which does have some overhead to it. It's not a fast plotting utility by any means. But a lot of this, like 40 minutes, so like that was about the overhead for kind of these like 4 to 5 minutes things that when it took 40 minutes, that was really the slowdown of how accessing these files on the cloud storage without doing anything. That was kind of that shows like it's a, 10 times longer just to like run this workflow and like actually pull the data when we need it. That part takes a long time. And since Xarray loads it lazily, every time you do like make a new plot, it has to re-pull that data down unless you specifically tell it to like store it in memory or something. So yeah. Okay, this is almost done. So once this is done, I'm going to start going, but I'll go a little slowly, since I think some people here aren't super familiar with Python. We'll go through this a little slowly, and then hopefully people can catch up once the build here finishes. Oh, Pangeo is back up. I recommend you try using that if you can, but if you're already on here, the image is built and is pushing, so that should be done really soon. But hopefully we don't all crash it again. We'll see. So the first thing I want to do is import FSpec reference maker and just check that we're on the latest version. Currently, this is still very, very early software, so the latest version is 0.0.3. And then we're going to pull in a few other libraries. Xarray is a utility used to kind of work with these types of gridded data sets. It works really well opening netcdf files. It also has ZAR functionality built in, which we'll use later. Matplotlib.pyplot is kind of the Python standard plotting package. from FSpec Reference Maker, we're going to import a couple different classes. This one is used to make a single reference file from a single netcdf file. And then this one takes many reference files and combines them into one. So essentially making a big data set that covers many actual files and making them as if they're one file. And I'll show how to do that too. The other important thing is FSpec, which is kind of the parent project for Reference Maker. What that is, I have a little blurb on it here. It provides a unified interface for different file system types, whether it be local file systems, cloud storage, HTTP, Dropbox, Google Drive, kind of makes it so you can access files on those services, all with kind of the same syntax. So just for a little fun here, I'll show the known implementations. These are all the different types of file systems and storage media that FSpec can handle. So what we're going to do with FSpec is we're going to initialize a new file system of type S3. S3 is Amazon Web Services object storage, which is like their big cloud storage provider. And that's where most, if you see stuff that's like, oh, we put our data in the cloud, they put it in object storage. In Amazon, that's called S3. So we're going to start, oops, I, of course, didn't actually run that import block. Beth, if are you on the binder page on the Pangeo? Yeah, you should be able to run interactively. It should.
I think this is more of just a getting used to using notebooks question.
Oh, sure. Yeah, so for the notebooks, it looks like the binder is up to. The binder looks a little different. The interface looks like this, but if you click on that, it'll pull it up in something similar. So for the notebooks, each cell is kind of a snippet of code. You can hit Shift and Enter to run that cell and move on to the next one.
There's also a play button in the top panel. But
oh, okay, good. Looks like it. Yeah.
So you want everybody to open up this 01
Yep.
file.
Yep,
yeah,
that's right. So everybody open up the 01 file and then scroll past all the jargon that I wrote on the top of it. Okay, so if anybody is like far behind this, please let me know. But hearing that at least one person got it to load, I'm gonna power on here. So we're gonna start a new file system, just telling it to expect Amazon Web Services S3, and this is a public data set, so we're going to use anonymous mode, meaning we don't need to provide any credentials to actually pay for any of the data. Then we're going to use, this is part of FSpec, kind of those unified operators. We have fs.glob. Glob is a utility that just kind of lists files and directories. And so the NOAA GOES 16 satellite data is arranged in, we have base directory here. This is our product. So this is the sea surface temperature. And then the year, and then the day of year. So this is the 210th day of 2020, or July 28th. And then for each one of these subdirectories is an hour. And then within that hour, there's data files. And so giving two asterisks here tells it we can pull whatever, like take all of them. So take all the hours and take all the files and all the hours. So if you run that, it takes a sec, but you'll see here, it has an asterisk while that part is loading, and then it changes to a number once it has run. So we're going to take a look at just what the first entry in this list looks like. So we have NOAA GOES, sea surface temperature, the 210th day at 0 hour, and this is the first netcdf file we have here, and that's a .nc, which is a common ending for netcdf. Though a thing we do want is to have the S3:/ at the beginning of it. So this line here, it takes that and it adds it to each file in that list. So if we run that and run it again, we'll see here's the first 3 files now have kind of the full URL like that. Any questions so far? Because now we're going to get into the real heavy stuff.
Just want to check real quick if everybody's caught up now. You could give us a thumbs up or a thumbs down or whatever the other reactions are.
Okay, cool. Good to hear someone else says Binder is working. When it comes to Binder, this next part is not going to work as well as Pangeo. So just as a heads up, the reason I want to use Pangeo is it gives you more RAM and more processors per notebook. And so we can actually use Dask properly, but it'll still work. It'll just be a little slower. So what is Dask, as people are kind of getting caught up? Dask is a Python package that just makes it really easy to parallelize code. Turns out generating these references, we don't need to do them in order. We can do a bunch of them at once if we can. And so this is a really easy way to do it. Don't worry too much about the actual code part of this, but what we're going to do is we're going to run this cell, give it a second. Oh, this is where, if I'm doing it on Pangeo, maybe I'll switch over to that real quick. If I do it on Pangeo, it actually works better. If you're working on Pangeo, once you run this Dask section right here, if you click on this little orange icon on the left and then click on the magnifying glass, it'll like make these buttons orange. This doesn't make any difference in terms of running the code. It's just kind of fun to see. If we click on, I click usually on progress and task stream. And what I do is I just drag them over to the right-hand side and kind of stack them on top of each other like that. You don't need to do this. If you just want to watch along on my screen, that's fine too. But what this does is it shows what Dask is doing. So what Dask is doing here is we've started 4 workers. And these workers can work in parallel to run a function. And since for generating a reference, we can do 4 at once, essentially, is what this allows us to do. So here's the meat of Reference Maker right here. We're going to define a function to take in one of these URLs that we defined right here and generate a reference file for that. So this function, it takes in a URL f. There's a few options here. Don't worry too much about them. They're just needed to kind of get everything working. But then we use fspec to open that file, the URL. And then this is just giving it all these options we defined above. And we're going to call that file in file. And then this is part of Reference Maker right here that I imported above. It takes that in file and it takes the URL. And then we run .translate on it. And what this does is it returns a dictionary, which is kind of a Python way of storing keys and values. It returns a dictionary with the references to that file. So right now we could just give it any f. So if I do, you don't need to follow along for this, but if we do, we have flist 0, this is one of our URLs. If I do gen ref of just that one URL and give it a few seconds, it's going to spit back a big, ugly dictionary at us. This is why we want to do it in parallel, because doing each one of these one at a time would take a long time. So here's this like kind of all this metadata on this file. We'll use this later, but right now what we want to do is we want to get kind of a list of all these files. So another thing, again, don't worry too much about this. It's just a way to speed this whole process up. I'm going to use Dask bag, which is a way to kind of tell that list of files that I want to run a function on each one of those URLs. So I'm giving it the list of files and I'm telling it to divide them up into as many partitions as there are files. So one file per partition. Don't worry too much about this thing here, but what's cool is we can do a .visualize. And we see here, this is each, so there was 24 files or 25 files, 24 files, and they're listed 0 to 23. Each one of these is then gonna run genref and then return the value of what we returned here. So that big dictionary. And this is where this right-hand side comes into play when we tell it to compute those. That screen on the right here, if we give it a second, I think things are running slowly because everybody's using it right now.
maybe you want to talk, take a sec to talk about how people can run this in other places, or where they might want to run this when they're actually doing work as opposed to demoing.
Yeah, so the kind of the idea behind this is that in the future, in the big future, you don't have to do any of this, and a data provider will have these reference files generated for you already, and you just need to access them. What we're doing up front here and generating these references is a one and done thing. Personally, I generate them within a Jupyter Notebook environment just like this, but I usually run it either on my own machine or on a actual compute cluster. And that way you can use more processors to generate more of these references at once. But once they're made and once they're saved onto the disk, you don't need to do this process ever again for that data set. It looks like we're possibly crashing Pangeo again. So I'm going to stop it on my end because I thought ahead and saved some to disk. So one of the things that I did on this repository is there's an example JSONs folder here. Inside that, there's a folder called individual. And inside each one of these is a JSON file, which is the reference, metadata reference for each one of those NetCDF files. So if I open one of those up, this is the same thing that we saw up here, except kind of presented in a neater view. So the things that it has in this file, it gives you the URL of the file, some of the attributes and the text metadata that is included in the file, things like the chunk size, what kind of compression was used, the shape of the files and all that. And then so for like DQF, which is the data quality flag, this is one of the variables. This is where it's telling you, so this is chunk 0.8. And this is that byte offset saying it exists between byte 1375 and byte whatever, big number. And so what we can do is we can actually just load those in. And what I'm going to do is I'm going to uncomment this second thing here and run that. And this gives me the same output as this, except it seems like our compute is not working properly because we're overloading the server. So if you're also having problems and this cell right here isn't actually doing anything, feel free to uncomment this this cell right here and run that. And all that's doing is it's going through each one of these files, converting it to a dictionary and appending it. So now if we do, if we look at the length of that dicts, there's 24 individual dictionaries on there. Michelle says hers is working again. Oh, I'm sorry. I did that really fast, Naomi. To uncomment block, it's control slash, the slash next to the right to the left of your shift on the right. If you select everything and do that, it comment or uncomments the block, which is much easier than going in and doing it individually. But yeah, if you're able to actually generate them using the bag.compute, please feel free to do that. But for the sake of time, I'm just going to keep going this way. So right now, if we, there's 24 dictionaries that we've generated. If we do, if we just look at one of them, again, it's this kind of messy metadata that we don't really need to look at ourselves. But what we can then do, and if you're used to using NetCDF and Xarray, you're maybe familiar with the idea of an MF data set, a multi-file data set. And so, here we have 24 hours of sea surface temperature. If you're a data scientist or an oceanographer or something, and you're looking at this data, you probably want to have access to all this 24-hour data set at once. You don't want to have to go in and individually open each file and find the data you need, close it, open the next one, right? So what we can do is we can actually take all these individual reference dictionaries and kind of squash them into one. And then from that point forward, we can take this entire 24 file data set and treat it as one file and one data set. And so the way we do that is with this other utility called multi-zar. This takes that dicts list, which is just a list of each reference dictionary. We can also give it just a path to files. So if we wanted to, we could tell it to like list out all the files here and just give it like the path to each one of these files. It also knows how to understand that. And a couple more things, just like we did before, telling it it's Amazon S3 and that we're going to be running it in anonymous mode. And then a few things to X-ray to kind of speed up the process. And then importantly, this is a thing you kind of need to know ahead of time. The time dimension on these is called T. And so I'm telling it I want to kind of concatenate all these along the time dimension. I'm going to go back to the home folder here because we're going to have a file pop up. So I'm going to initiate this. It doesn't actually do any processing. Once you do that, just kind of gets all the pieces into place. And then from there, you just do MZZ, which is what I called this kind of function here, dot translate, and then give it a file path. So in this case, I'm just going to write out to a file called combine.json. And if I run that and I give it a second, it doesn't take too long. And then I refresh the files here. There it is, that file we just generated. And so if I peek into this real quick, whereas before, if we take a look, like there was just one file, this one now has all 24 files listed. And so when we read this file, if it needs to know, this is going to be much more messy. If it needs to know, yeah, see, these things get really gross. So if we need to know, like, we want to get a certain chunk of this data quality flag, it'll know which file to pull that from, and we only need to think about it. So the important thing here is that everybody has this combine.json before we move to the next part, which is reading in that that metadata and actually accessing that data in the cloud. Right now, all we've done is just kind of generate the metadata that we need and kind of made it into a file that we can share. We can send this to somebody. Once it's created, it can be used by anybody who knows how to actually plug it into the system and get it to read the data that way. So I'll pause here for a sec and see if anybody has questions, or if we need to wait a sec to keep going. Okay. Hearing nothing, I will keep going here. So I'm opening up that next notebook called 02plotting.ipynb. This is another part. If you're going to be running this on Binder, this will probably crash the Binder instance because this takes up a little bit more RAM. But I'm going to show off a couple different ways to plot this data and a couple tools to kind of make accessing it a little easier. So I'm going to import a few different libraries this time around. I'm going to import METPy, which is a package developed at Unidata at NCAR, the National Center for Atmospheric Research. It's used for kind of utilities for atmospheric and meteorological data. So it does a few things with our data set that will be really nice to use. Another thing I'm going to use is HVplot, which is a HoloViews plot. I'll show that off in a little bit here. It's a really cool way to plot data interactively in a notebook. I'm also going to show how to plot this just using matplotlib, which is the more common Python plotting package. We're going to need FSpec again and Xarray. And then CartoPy, which is a Python cartographic utility. This is going to deal with transforming between a couple different coordinate reference systems that we need to use for actually plotting the data. I'm going to close out of these here. So first of all, we need to access our data. I accidentally pasted in there. So what we need to do is we need to create a new file system, just like we did up at the top of the first notebook. Here we told it it was going to be S3. This time we're going to call it a reference file system, and that's where the term reference maker and reference file system come from. We're going to tell it that the reference for that file system is that combine.json. If for some reason you weren't able to run and generate this combine.json, I did add one inside the example JSONs folder. So if you uncomment this top line and comment the bottom one, this just changes that file object to use the one that I already included in the repository, just in case something went wrong and you weren't able to actually generate this file. And then again, we're gonna tell it that's S3, and we're gonna use anonymous mode. And then another option just to kind of speed things up a little bit. I'm not actually too sure what this does. I've just been told to use it, and I don't question that. So we're going to do that. Oops, of course, I forgot to run the import again. So we're going to run this. This just initiates the file system. This is where we actually open the data set. So if you know X-ray, this will look very familiar with you, to you. You do X-ray.open dataset, and instead of giving it a file or a path or something, we're going to give it this file system .get mapper with an empty kind of quote in the middle there. And we're also going to specify that we're going to use the ZAR engine, because this is a that metadata JSON is in the ZAR specification. Another thing I'm going to tack on to the end here, this is where MetPy came on, is it takes the information on the projection information from this satellite and actually translates it into something we can use a little bit later. So this is kind of a way to speed things up and make things easier for ourselves later. Another thing I'm going to do quickly before I print out the data set is I'm going to change the long name of the time variable to time. Otherwise, it's J2000 epoch midpoint between the start and end image scan in seconds, which when it plots automatically on a plot, kind of takes up the whole space. So keep in mind here, if you're used to running open MF dataset, this process can usually take a while. We're about to open 24 full disk image captures of sea surface temperature. This is a process that would normally take tens of minutes in normal ways, but I'm going to hit enter here, and we're going to give it just a couple seconds, and there's our data set. So if you're kind of used to this type of workflow, this will be, I think, a little mind-blowing on how quick that was. So we have all 24 times here in our T variable. So we actually did merge together all these data sets together. And then our data is 5,424 by 5,424 in an X and Y direction. And then we have a few data variables. The ones we're concerned with is this one, which is sea surface temperature. A bunch of other things that are different kind of retrievals that we're not as interested in with this. Any questions up to this point?
I was just going to comment that at least I'm seeing a little bit of delay between when you do things and when it shows up. So you might want to wait a little longer between each thing, just so that we
Sure.
actually see what happened.
Yeah, absolutely. Sorry about that. So yeah, there's a little bit of warnings because we're not actually using ZAR itself here. So this warning will happen every time here. And then here is our X-ray data set. We can kind of take a look at, the dimensions. If you look at, say we want to have information on sea surface temperature under data variables, we can click this, which kind of gives more attributes, units of Kelvin, what the resolution is, the long name of that variable, and then different kind of different metadata that's available on that variable. So now what we can do is I can say that SST, sea surface temperature, is our data set SST variable. And then our coordinate reference system is our variable .metpy.cartopy. That was what we did up here with the .metpy.parsecf. I'm sorry, I completely forgot that when I moved to this, I didn't do presentation mode. So let me make the text a little bit bigger here. So this is what this did, is it allowed us to kind of generate a reference system for the coordinates. And so this is a cool thing. If you were into Python but haven't heard of hvplot, I think this will be really cool. What we're going to tell it here is we're going to take our sea surface temperature variable. We're going to do an hvplot.quad mesh, which is just kind of a gridded image view of our data. Give it the names of the X and Y coordinates, which for us is just X and Y. I'm going to give it the jet color map. Since we're looking at temperature, it's cool to see like the reds are hot and the blues are cold. The cool part of this, I can say group by time, and I'll show you what that means in a second here. But then also I'm going to say our coordinate reference system and our projection are both CRS. This one is telling you what our input coordinate is, and this one is telling it how to project it. We're just going to use the same way. That way there's no need to recalculate any of the coordinates. And we're going to give it some information. We're going to project it. We're going to give it coastlines, rasterized. This makes it go faster. And then this is just a plotting limit. I just want to view. I just want to color data between 220 and 320 degrees Kelvin. So I'm going to hit enter. This will take just a moment. Yeah, Michelle is a little bit ahead of me here. This is the cool part of the whole presentation. So what we're doing here is now it's actually going and pulling in the data. Before, when we did this part here, all it did was pull that reference information. But now we're actually pulling in the data and plotting the data. So this takes a little bit because it actually needs to go and download the data it needs here. This is another thing that might go a little bit slowly if everybody is hammering the Pangeo cloud. So yeah, here we go. So here's our full disk image of the United States, or of the eastern part of the Western Hemisphere. And what's cool about this HV plot is it's fully interactive, so you can hover your mouse over and get the value. So like right here, we're at 302 degrees Kelvin. But you can also, if you click on this little box zoom and then drag and drop over location, it looks a little jagged at first, but it's going to continue to pull that data in the background. And there we go. The resolution kind of snapped back in there. Now, the really cool part of this, and this is where I said that group by equals T works. Yeah, there is lag involved in this because we have to, every time we move the image around, it has to kind of re-download the data that's needed. And we're also kind of bombarding the Pangeo servers with this too. So there's a bit of lag involved in that. But this group by time, we told it we want to group by the time coordinate. And what this did is it created a slider over here that we can then drag across. So let's say I want to plot actually at 12:30 UTC. And to drag that over, again, you have to wait a second because it's gonna have to re-pull that data down. It updated just a little bit. It like jumps an hour and then hangs and then jumps the rest of the way usually. There we go. So yeah, that's a way that you can like kind of go and play with the data. You can then, kind of move around here. What was interesting here is you notice it only pulled the data in for the area we were looking at. And that was where knowing the chunks of the data and what chunks of the data to pull for a certain view really helps. So now that we move the map a little bit, it's going to go and re-download that information. So it's only downloading the data that's actually needed. Oh, the lag is with the sharing the screen. That's what Alex was talking about too. Okay, sorry about that. I will do my best to kind of slow down between when I say something and when I do something.
Yeah, I think the other thing is when you reference a particular cell block to name it in terms of what it is, as opposed to saying something like this or that. Because
yeah, I'm sorry. Absolutely.
That's okay.
That would be very difficult to do if there's a little bit of a lag.
The other thing that I was just thinking of that I was kind of curious if you knew about is I know some people have been experimenting with creating overviews in Zarr, which are resampling of data at different resolutions in order to sort of pre-cache rendering. Have you tried any of that?
No, I haven't yet. I'm not too sure how that would work in the system because we're not actually modifying any of the data directly. And so I don't know too much about that kind of aspect of Zarr, but I would imagine like if it's resampling the data, you have to save that somewhere, right?
Yeah, I guess what I'm kind of thinking about is if you could generate that like when you're generating the reference maker index so that it's still not having to make a complete copy of everything in Zarr, but maybe it's making at least a few different zoom levels ahead of time, because usually those are a lot smaller.
Yeah, absolutely. I think that's totally possible. I'm not super familiar with, working on this project over the summer was kind of my first introduction into Zarr, so I'm still learning a lot about kind of its use case. But the goal for this project is to essentially, at this point, like HoloView is an X-ray. For all they're concerned, we're accessing a Zarr store online. And it's all that work it kind of disguises this netcdf as a ZAR file. And so theoretically, a lot of workflows that work to kind of optimize ZAR should work with this. I'd be really interested in talking to you more about that, because I think that'd be a really cool kind of feature addition to add to this and try it out with that. So I'm going to scroll down a little bit here to that plot with matplotlib section. This is a plotting package that more of you are probably familiar with. That's kind of the Python default. And here we're going to do a couple more things. So you'll notice that, actually, if I scroll back up real quick here, we're using the GOES X and Y grid, which is kind of, Naomi, are you on Binder or are you on Pangeo on that, on your URL at the top here? Is it binder.pangeo.io or is it binder.org? Yeah, if it's my binder, it doesn't actually have enough memory to render all these plotting. It's capped at 2 gigabytes, which really isn't enough to do much of anything. If you can run it on, try and go back and use the Pangeo link, that would work really well. You can then jump straight to that second notebook. The only thing you'll have to do, I'm scrolling back up to the top, that second block underneath the imports, if you uncomment that first line and comment out the second line, that'll tell it to use the already generated combined.json file instead of having to generate. With this data that we were using before, this plotting method, we were using the GOES X and Y grid, and those are kind of meters from the center of the GOES projection, which isn't a very useful thing for us to do. It's not intuitive. If we wanted to say, look at the East Coast of the United States, we'd have to do a bit of work to figure out what the X and Y coordinates of that are. So thankfully, another reason I imported that MetPy thing is using the GOES coordinate. The information it knows about the GOES projection system is it can assign a latitude and longitude to that data. So if first I imported matplotlib here, but then I run this cell right here where it says dot assign latitude longitude and give it a second. There's a bit of math that needs to be done here, and so it takes a couple seconds. Now under our, sorry, go ahead.
How does MetPy know that it's GOES?
MetPy knows that it's GOES because GOES adheres to the CF file convention, which part of the just like text-based metadata. So like if I click this here, it uses CF 1.7 conventions. And so I think MetPy checks this grid mapping attribute and it knows it's the GOES imager projection from there. And then from there, there's information like let me see, maybe it's not here, but there's things like the scan angles and stuff like that, that it can go and generate kind of latitude and longitudes from that information.
So the key here is that MetPy really works with things that are using so CF is a convention for netcdf formatting, right?
Right, it's for formatting and for metadata. Yeah, it kind of standardizes how you want to call your coordinates, what you should call your time, like your variables, how you should name like the attributes with each variable, like that long name variable and stuff like attribute and stuff. So it's kind of this list of conventions that if you can assume that those are being followed, you can actually get a lot of information from just a raw data file like this without actually having to generate it or figure it out yourself. So yeah, MetPy is able to kind of parse that information, and from there it was able to generate a latitude and longitude. Now you'll notice here it says that these are infinites, but the reason that is if we go back to our plot up here, it's this whole kind of square here. So some of the coordinates refer to areas outside the globe that don't have a latitude and longitude associated with them. So some of the lats and longs are going to be infinites on the kind of edges of the data set. But what I wrote here, since it's very easy to select based on X and Y, but on latitude and longitude, these 2D coordinates, it's hard to kind of subset by a range of those. What I did is I made a quick function that just takes, say you want to give it like a lat and long box. What are the X and Y minimum and maximum that correspond to that box? So all this does is it takes the X and Y and lat and long, and I tell it, just give me the biggest X in that box and the biggest Y in that box and the smallest Y and the smallest X. So what I wanted to do here is I'm just going to take, I want to look between 20 and 60 degrees north and minus 50 and minus 100 degrees east. And then from there, I'm going to find, oh, I didn't define that function. So from here, I'm going to run this. And based on that latitude and longitude, those are the GOES X and Y coordinates of those lats and longs. And from there, you can very easily say, I'm going to take a subset of that data. X is going to be a slice of X1 to X2, and Y is going to be a slice of, in this case, Y2 to Y1, because you have to put it in increasing order. And so from there, I'm going to put that there so we can actually see it. Before, our data set was 5424 by 5424. Now, when we did a subset, it's 2456 by 1451. So we're now looking at a smaller data set. And you'll notice here, I guess there are still some infinites on the latitude and longitude, but we actually get to see some of that data now. And so similar to HVplot, we kind of need to define some projection information. Transform is the coordinate that we need to tell it to expect our data in. And so in this case, we're going to use that metpy accessor .cartopy CRS tells it to use the X and Y from Cartopy and interpret that as the GOES projection. But we want to project out using orthographic projection. And I'm going to center that orthographic projection at 30 degrees north, negative 75 degrees east. From there, if you know matplotlib, we're going to just make a figure and then a subplot. We're going to tell that subplot to have that orthographic projection. And then I'm going to do a p-color mesh, which is the same type of plot as I did up there. Give it the X and the Y and the sea surface temperature. In this case, I'm just going to select the first time index. I know a lot of people here use R, so just a reminder that Python indexes from 0, not from 1. So just the first time index. So it's the 2D array with an X and Y, but then we need to tell it to expect that as the GOES projection, so we need to give it the transform. And just like before, a jet color map, and then minimum of 220 and a maximum of 320 in terms of our plot contours. Give it a color bar, and then tell it to plot a coastline, states, and borders. And also, this is just to make it zoom in on that portion. So if we run this, it has to download those boundaries and stuff, but there we go. We have the same looking map, except this is on matplotlib, so we can't move around with it, but that's, the more common plotting routine. So it's also very easy to just generate a plot from this data like that. And so that's really about all I had in terms of kind of example, like tutorial notebooks. I have one more notebook I wanted to show off quickly that shows like how much this can scale up to really, really big data sets. But before then, I just want to take a little bit of time here. If anybody's got any questions or wants to kind of see if something else is possible or something like that, I'm gonna sit here for a sec to let people fool around, or feel free to ask questions.
So how did you decide to pick your min and your max for your plotting?
I honestly just chose one that, if you notice that, like here we have, a sea surface temperature of, it says 220 degrees. Obviously, we don't have the ocean 220 degrees Kelvin. That would be ice at that point. That's obviously not what's happening here, but these are clouds, right? And so these clouds show up as, very cold sea surface temperatures. I just picked these values as a color map that was kind of like, showed enough variability in the actual sea surface temperature while also kind of making all the clouds blue. There was no huge reasoning behind those colors. If you leave that line out, it'll look a little bit different.
Yeah, I think I was wondering more in terms of, does the little meta display show you sort of the range, or do you often run like a histogram over a particular variable to kind of see what the distribution of a value is?
Yeah, you can certainly do that. I picked these. Well, I had a kind of an idea of, I can also, theoretically, we're not going to have, you can think of it physically as well. If we're interested in really just looking at sea surface temperatures, we kind of know a range of what those are going to be. And so, but yeah, you can also like going back up to the, to this, what's one of the really cool things like about this HV plot is you can kind of like look at the actual values of data points. So we can like, here in like the like the Caribbean and the Gulf, we have, sea surface temperatures around 302, but like down here in the Southeastern Pacific, it's 280. And so like we can kind of also just kind of look at and see, depending on what area you're looking at specifically, kind of what you want your max and min plotting colors to be.
Looks like we might be having a little bit of technical difficulties. If everyone wants to turn their cameras off, hopefully we'll save some bandwidth.
Yeah, it might be my internet has been kind of shaky recently, and I share an office at UC Davis, so I can't just like give a 2-hour workshop there. Otherwise, I totally would have. But I apologize if the internet hamsters are not running in their wheel fast enough to get the bandwidth up. Okay, well, if no one has got any questions so far, the last thing I wanted to show off here, this is not my notebook, someone else made this. A colleague that I worked with over the summer, Rich Signell at the United States Geological Survey. He's been kind of involved in this project from the beginning, and was kind of the ones who onboarded me and taught me kind of what I need to know and all that. And he's been kind of really interested in scaling this up to really, really big data sets. So I'm not going to go, this is just a thing to show off. I'm not going to go in too much into what's actually going on here. What I did want to show off is this intake catalog. Intake is a way to kind of, if I go back to the plotting notebook and scroll up to the top, it's a way to generalize this whole thing here and tell like and make it like this whole kind of opening a file system and accessing data. It's a way to make it so that user doesn't even need to worry about that much. So if I look at this National Water Model Catalog YML in here, this shows a lot of the options that we've looked at before. So we're using Xarray Zar source, so we're using the Xarray engine, Zar engine on Xarray. We're telling it it's a reference file system. Here is that target options, anon, true. Here's an S3 path and stuff like that. So it's kind of generalizing all that in the background, so that all you need to do as a user is say, yeah, I want to open that catalog. And then if we look at that catalog, there's like 2 different catalogs inside of it. There is, well, it doesn't show up on that here, but what we're interested here is a National Water Model Reanalysis catalog. So this here just brings it right into an Xarray data set. So this takes a little bit of time. This is an incredibly large data set. I think it spans 260,000 individual files, and is many, many terabytes large. So we'll give it a second here.
While we're waiting, what do you know about the Pangeo community and their work on making data sets available?
Yeah, so Pangeo, for those who don't know, it's a community of software developers and data scientists and geophysicists and all these groups of people who have come together to really try and make this kind of cloud-centered like data analysis workflow better and easier. So a lot of these projects are kind of supported by them and developed by them. And one of the things that they've been working recently, and I don't think it's fully public yet, but it's called the Pangeo Forge, much like Conda Forge for Python. It's a way for people to submit code that transforms existing data into cloud-ready data automatically. And so one of the things that we're trying to do here, and we've started working with them a little bit on this, is to make it so that you can just point that Pangeo Forge at a data catalog, and it'll do all this reference generation on its own. And so they're really working hard to kind of streamline this whole thing and make it easy for end users and scientists to just get from idea to data to science as quickly as possible without having to figure out where it's stored, how to access it, what code to use and all that. Just say, yeah, I want this data set and I want to do science on it. I want to do this analysis and all that, and just really making it possible to run that workflow as quickly and as seamlessly as possible. So now that that catalog is opened, let me open up data set here. Again, things are a little laggier on this notebook because did it kill the notebook? Yeah, it killed the kernel. I think it's because I've got too many other things running currently. Let me shut down the other ones, then redo this. Sorry about that.
So maybe another question related to this online notebook environment. Can you talk about the differences between data access time if, say, you're running the notebooks locally on your laptop and they have to go and get the data from the cloud versus the notebooks being in the cloud to begin with?
Yeah, absolutely. If you are, and we're not currently on the Pangeo binder, this notebook is actually hosted in the Google Cloud platform. They do have an Amazon Web Services one, but it's behind a GitHub login page. So I didn't want to have people to have to make an account if they didn't want to. So I used the one that didn't require a login. But yeah, if you are in the same, if your notebook is running on the same cloud hosting provider as the data you're trying to accessing, and especially if it's hosted in the same region, you're going to have really, really quick data access times. The further you get away from that, the slower it's going to be. If you're going to be running this on your home computer, for example, you're limited primarily by your home internet connection. And so you're not going to be able to download the data and access it quite as quickly. But if you are running this notebook on Amazon Web Services in the same region that NOAA has put their GOES data in, you're going to have incredibly fast connection to that data. And so what we're trying to do, the eventual goal is that like this kind of co-location of data and of computation is going to become very, very easy. And you just like you just hit a button, it spins up a server for you to use. And then from there, you can just very quickly and very easily access that data with almost no overhead whatsoever. So, okay, that opened and it didn't crash this time. So this part right here is telling us that this one variable in this data set is 8 terabytes large. So this is a very, very large data set. Normally, you know, trying to access a specific variable across a set of times or a specific time, it's a hassle. You have to figure out where the files are listed, which ones contain what information. But instead what we're going to do is I'm just going to take this data set that we already created. I'm going to say, yeah, I want this day. And it uses the nearest method in case there's no data actually available at this time. It'll just take the nearest available time. Yep, I want that time. I want the streamflow variable. I want to convert that to a pandas data frame. Here he just does a couple things to change the title. And then I'm going to hit this. This will take a couple seconds using hvplot again. And this is National Weather Service streamflow data for modeled streamflow data for the United States. So here we are with a map of that 1 day of streamflow data. We can then, you know, let's zoom in. Oops, let's reset that. You're limited to the aspect ratio that you started with. And so easy as that, we're kind of like accessing this incredibly large data set and being able to zoom in and get the data that we're most interested in, you know, quickly and efficiently without needing to download the entire data set or entire files. Just get the chunks that we need that way. So the idea, like the end goal behind this project is that, you know, we have, say, one of these intake catalogs for the entire GOES satellite archive. And so as a user, all you would need to do is say, yeah, I want to open the GOES catalog, and I want to plot the, you know, sea surface temperature on this day over this area, and it can just very quickly go in and kind of tunnel through all the different files and all the different data and pull out exactly what you need and send it straight to you very, very quickly. So you don't need to go and request certain files or go through a web page that kind of has you figure out what times and what lats and longs you need. Like everything's just available directly within your Jupyter notebook. All right, that's all officially for all of this, but I'm happy to hang out here for as long as people are interested to talk about this, or if you have questions or have we're trying to do like some of your own code on here and it wasn't working, I'm happy to like help take a look at that or whatever. So yeah, whatever we want to do with the rest of the time here.
Well, thank you very much, Lucas, for sharing all of this with us. I am very excited to try out some of this stuff later as well. I apologize earlier. I hope it didn't cause problems. I got booted off of Zoom. I was really worried. So
I think it was all good. So.
All right, great. So what I'm going to do is I'm going to stop the recording, and then we can have a discussion with everyone that's here.
Sure.
Let me go ahead and do that.